All right, I would like to thank the organizers. I'm very happy to see this community grow. I gave my first talk here in 2003 when I was a grad student. I was totally freaked out. And so I know what it feels to be a grad student giving your first talk here. And so I kept my title a mystery because for a while I was debating what to talk about. And I sort of settled on a topic which is in many ways a bit conservative for me because I've been giving talks about a similar topic for the past couple of years. I just released a sort of survey, and this talk will look like a survey as well. I'm going to give you an overview of the work we've been doing around transformers, where we developed a model. And this is now a somewhat long line of work that I started with my colleague at MIT, Yuri Polyansky, and at the time, Boyan and Cyril were postdoc there. And since then, a bunch of postdocs and students have joined us in this effort. And I'm hoping to demonstrate in this lecture that there's really a lot of interesting questions to think about in this model. Maybe not so much statistical for today, but it's a pretty rich model. I'm sure you will be able to come up with some interesting statistical questions. We're thinking about them right now. And there's many things you can really try to think about. So as I said, there's a variety of work that we've been doing. These are the ones I will talk about today. In fact, I was not able to fit everything on this slide. So we started with that first paper over there. Today I will focus mostly on essentially, I will talk about all these models, but if you want to read about this, really those two papers are more survey style. This one is the proceedings of the ICM talk I'm going to be giving next year, and that's really high level, and this talk will essentially be like this, so hopefully you won't be too tired for the coming talks. So let's start with a sort of a very brief and incomplete history of neural networks, starting in 2012 with Hinton, Krzyzewski, and Suskever coming with their AlexNet architecture, which sort of revolutionized and started the AI revolution or deep learning revolution in the area of computer vision, where they really beat everyone in this ImageNet competition. And since then, there've been some developments, and I have to admit, personally, at first, those developments I was not particularly sensitive to. I thought, neural networks are just a great model for natural images. So what? It's not like we explain why wavelets are better at compressing images, or, it's not so mathematical that I could say something about it. And then starting, with ChatGPT in 2022, I started being quite impressed with what they were able to do, and I decided to start thinking about these questions. And one of the things that you will see that is really a shift in this series of architecture is the introduction of the transformer architecture in 2017. And so it came in this paper from Google by Vaswani et al. And this transformer architecture, which I will describe in a second, has had a massive impact first on natural language processing. So it went beyond images and started talking about natural language processing, or NLP. And then it was subsequently folded back into vision. So Yushin talked about it at the beginning. Now, if you look at a lot of the generative AI for images, there's also some transformer layers hidden in there. It's also had a massive impact on paper titles, where people started using is all you need at the end of every single one of their titles. So you could have a minimax optimality is all you need. You can do whatever you want. If you don't have something that's all you need, you can also do it's not all you need. It's okay. And if you're really not sure, you can do some questionable grammatical things like not all attention is all you need, which really doesn't mean anything. So what are transformers? So transformers, actually, this is a partial picture, because if I actually pull out the full picture of transformers from this paper, there would be another thing on the other side. So this was for machine translation, and there was basically one column for one language and one column for the other language. And since then, it's really that left column that really matters. And that's the at least for what I'm going to talk about. In fact, the other column is more important for ChatGPT. When you generate text in an autoregressive fashion, this is for embedding. And I'm going to talk about this encoder style, and I'm going to start telling you how it works, right? We're going to break this down into pieces. And so the first thing that matters for us is the tokens, okay? So you're going to start with the inputs. They're going to be typically sentences, and you're going to first turn those tokens into, these sentences into tokens. The way that works, is as follows. You start with your sentence, and you're going to break it into words or pieces of words if they're too big. And so that's according to some tokenizer. And this tokenizer is going to embed each word into a vector. Okay, so for example, the word lazy is going to go to a particular 512 dimensional vector that's just given by some dictionary that's either learned or completely random. It really doesn't matter anymore. And then they're going to slap onto this typically a positional embedding that tells me in which position the word lazy showed up in this thing. And when I concatenate those two informations or add them, there's many ways to combine them. I'm going to end up with vectors in RD that are called tokens and that contain not only which word it was, but which position it came up in the sentence. All right, so this is the input to those things. Now I have bona fide vectors, and I'm going to start processing them using formulas. So now I could do this for an image as well. So I just showed you for text. So the thing that really matters, the thing that was really showing up is this attention thing. That was the title. And so this attention is, so here I'm describing one head. And so it's this formula. So what it does, and we'll parse it a bit more later, but essentially what it says that each token will receive itself plus something which is called the residual stream. And the residual stream is a weighted average of the xj's that are pre-multiplied by some matrix VL. L here indexes the layer at which I'm talking out. And so I'm going to repeat that thing. So for each layer, there's a set of 3 parameters, the query key and value matrices that I have to learn from data. Okay, so that's the most important part. And I'm going to think of this as some interacting particle system because as you can see, xi depends on all of the xj's. Okay, it's not in a complicated fashion, but it depends on all of them. And that really is what's changed. When you're looking at what's called multi-layer perceptron, I'll talk about them in a second, the one that has the usual ReLUs, each token is processed individually, right? You take this sigma of ax plus b, and that doesn't matter what the other words are. And here we really have to have them interact with each other. Another thing that shows up is this added norm. So it's some normalization layers. There's many variants. We'll come back to it towards the end. But in a nutshell, the idea is to say, I don't want those tokens to fly out to infinity or to shrink down to 0. So I'm just going to normalize them. And it's enough to think of them as being just projected on the sphere. Okay? So you just take your tokens every time they're moving all over the place, and then you project them back on the sphere. And then there's this feed forward. So those are the so-called MLP or multi-layer perceptron layers. And they're the usual ones that we've seen over and again since 2012. Those are the building blocks. I mean, there's some convolutional layers that are dedicated to imaging, but the processing layers are really those things where you take an affine transformation of each individual token and then some nonlinearity like ReLU, so the positive part that you add to the previous one. Okay, so I'm not going to talk too much about this because that's more ancient history, and I will focus on the attention, which is really what I want to understand. So this is each block does this. That's essentially what's called an attention block. It's the combination of attention, normalization, and MLP. I'm going to put them together. So that's 3 layers, but I want to think of them as a block, and I'm going to repeat this. And here, usually we use the word capital L, but in that paper, they use the word capital N. So I'm going to repeat this for N blocks. So you want to think of them as like, blocks of 3 layers. We'll see, for example, an example where we have 48 of those. Okay. So the question I'm going to be asking during this entire talk is, how does this process information? I started from x1 to xn, and I'm going to repeat that thing. Something's going to happen to those x1 to xn. What is happening to those x1 to xn? Okay, that's the question I'm going to be asking. And it's a difficult question, right? I mean, at the end of the day, I can do this to actually find what the next word in a sentence is. There's many different things that are happening, but I want to ask it more as a sort of high-level view. Here it's going to be almost a topological question I'm going to be asking. So I have a set of points. What happens to that set of points? So let's see what happens in some real example. So what we did is we took some input. Here the input is some random page on Wikipedia for this RAF fighter jet. And what we wanted to know is what happens to the tokens, okay? So what I'm going to try to show you is that those tokens tend to cluster together. So to illustrate that, and by the way, this is an interesting question. We realize there's no real methods out there for that, is how do you measure, if I give you a certain set of points, how do you measure to which extent this set of points is actually clustered? And so the thing we came up with is the following. We said, okay, those points are on the sphere. So if I measure their inner product, if they're in the same position, I'm going to see a 1, and if they're in some random position, I'm going to see a 0 for this inner product, essentially, right? It's a high-dimensional sphere. And so I look at all the n choose 2 possible pairs, and I form the histogram of those pairs. And you can see it's basically a Gaussian with a little bump here because essentially the punctuation is encoded slightly differently, and so it goes in its own place. So, but if you look at the bulk, it's centered at 0, almost symmetric. What it means is that they're essentially randomly assigned on the sphere at the initial layer, okay? And so now I start at this 0th layer, that's my input tokens, and I want to see how it evolves as I process this thing through a trained transformer. So the transformer we're looking at here is called Albert, named after Stas's son. No, I'm kidding. It's named after BERT, which is a Google transformer, and the AL means A light BERT, right? So light version of BERT where the weights are tied through the layers, and that allows us to basically repeat the layers as many times as we want because it's always the same layer that you apply. And so we just applied 5 times that layer that was trained by Google, and what we found is that already this histogram is shifting to the right. What it means, if you can see, basically all those inner products are positive, right? So everybody's basically within the same hemisphere at this point. And then I keep going, and this thing shifts to the right, shift to the right, shift to the right, keeps on shifting to the right. And you can see this point mass at 1 that starts developing, meaning there's a bunch of tokens that are actually in the same position, right? Their inner product is 1, they're on the sphere. And those spikes here, they're measuring the inner distance between 2 clusters, right? So there's at least 3 clusters here, because I see at least 3 choose 2 peaks, but I don't know, maybe they're equidistant to each other, and I don't know, but there's some clusters. Clearly there's some clustering happening, right? And I can really see that when I started from something that was basically random, the thing that happened that I can really see is this clustering. And so what I'm going to try to do is to explain this. And the model is very complicated, so I'm going to try to find a simpler model that sort of simplifies this attention thing and removes some of the bells and whistles and still captures this idea of clustering. And then if I find the right model for this, maybe I can study it for further questions. And so the model we propose is called self-attention dynamics, and it works as follows. So we start with the attention head. So this is the same thing that I described. And as you can see, so this attention head, as I said, has 3 matrices. They're typically D by D matrices, where D, in the example I can run on my computers, are typically 512 dimensional. So that's 3 sets of such matrices, 3 such matrices per attention block, right? So here I showed you 48 blocks, so I have a bunch of those things. And the other thing that actually turns out does matter for us is this layer normalization. Okay, so pictorially, I'm on the sphere, I have xi that's on the sphere. I push it by this velocity field, which is this sort of, depends on all the particles, right? I say xi is xi plus this velocity, this vector, and then I'm doing a retraction and projecting back onto the sphere, okay? So those are the 2 things that I'm doing. And so I'm not going to talk about MLPs at all. MLPs are sort of believed to store information about the data set. So people have made a lot of experiments that way. So the people like to think that the thinking of the transformer happens through attention and the information retrieval happens through the multi-layer perceptron. So I'm not going to mention the MLPs. And so the way I'm going to idealize just that part is by actually taking, first of all, thinking of this xi plus 1 is xi plus something as a 1-step discretization of a continuous dynamics. And the second thing is I'm going to remove those 3 matrices because they can really be anything, right? They are trained from data, and I don't know what they are, and I'm not going to make a study for some given random set of matrix. And so I'm removing that guy. And so what happens is that now I have this much simpler dynamics, right? There's no matrices. I only kept this beta parameter, which is something that measures the locality of which token I want to interact with. I will parse this in a second. This is the projection onto the tangent space of the sphere at the point I am, right? Because when I move outside of the sphere and I project back, when time goes to 0, what it means is I'm forcing my velocity field to stay on the tangent space of the sphere so that I can only live on the sphere. So now I have, each token is a point that's just moving continuously on the sphere. And so the velocity field that it's subject to is a weighted average of all the other tokens, and the weights are proportional to exponential beta times the similarity between token I and token j. All right, so the way I want to think about this is that if xj is close to xi, it's going to get a large weight. If it's far, it's going to get a low weight. And the sort of cutoff, the bandwidths of this thing, if you want to think in terms of kernel density estimator, and I'll come back to it towards the end of this talk, is going to be governed by beta. So h is actually 1 over square root of beta in that case, right? So the standard deviation of this sort of thing is 1 over square root of beta, so it's only sort of averaging things that are at scale within 1 over square root of beta of me, okay? And so this is a butterfied mean field interacting particle system. There's lots of literature on this, and that's we're going to try to leverage that. So when I say mean field, what do I mean by mean field? What I mean is that I could have any crazy function of all of the xi's here, right? That's an interacting particle systems. All of the xj's, I could just have them interact in any way I want. But the fact that it's mean field means that it's actually very specific. The way I want to see this, so divide the numerator and denominator by n. So what this average is, it's really an integral against the empirical measure of the xj's, right? And so this average is just an empirical measure. And so here it's much more transparent. What it says xi, so that should be xi dot, is the evolution of xi, so it's the projection, so that's just to stay on the sphere. But it's really, and that should be an xi, so it depends on itself and the measure of everyone else. That's the only thing that matters, just the measure, all right? Not just token I and token 22, it's just really the empirical measure that matters, okay? And he's doing some sort of average. In fact, it's almost linear. If I didn't have this denominator, it would be linear in this thing. And so just to massage this a little bit, if you look at this, so this projection is a, so when I look at the projection, the gradient, the Riemannian gradient on the sphere is just the projection of the Euclidean gradient, right? If I asked you, what is the gradient of a function when I only am allowed to move along the sphere, you would compute your vanilla gradient like you do for Euclidean case, and you would just project that guy onto the tangent space. So when I write this gradient, this nabla sign, it's actually just the Riemannian gradient, and it's just the projection of the Euclidean gradient that you know, okay? And so, but what's nice is that, okay, so what is the gradient of the log? Gradient of log of f is f prime over f, right? And so if you see, this is exactly what it is up there. It's f prime over f. And so this, in fact, is x dot is moving according to the gradient of the log of the integral of this exponential thing against d mu. Now I'm going to massage this a little more. X and y belong to the unit sphere. And so this is really just a cross product in some squared expansion. And so I can, up to some factor 2, it's the same thing as just looking at the square distance between x and y. And now you can really see how I'm down-weighting things that are far from me. So x is putting some weight on y, which is essentially a Gaussian weight. So I'm on the sphere, so it's not quite Gaussian, it's a Gaussian on the sphere, but I'm basically exponentially down-weighting with some Gaussian kernel that we all like and know. And what I'm doing is I'm saying, okay, the direction in which I'm going to move is I'm going to form this sort of kernel density estimator. I'm going to take its log, and I'm going to move according to the gradient of this kernel density estimator. Right? So think about it, just take your kernel density estimator and you're trying to go up. Yes? Yeah, because now I'm mean field. So everybody's moving in the same way, so I don't have to write I. For all I, it's going to be true. Oh, mu is always, so mu is the law of a random x, of a random x from mu. Sorry, x is so mu is the law of x, if you will, or x is a random choice from mu, if you want. Other questions? Okay. So I'm at this point, so let's just put it on top. And so this is where I got hooked on this, because I see this and I see, so I'm not going to have time to talk about this, but if you see this, you see that x moves according to the gradient of some function of mu, of some functional of mu. And that feels very much like it's going to be a Wasserstein gradient flow. That's what Wasserstein gradient flows look like. You're moving particles according to the gradient of the first variation of a functional. So we all know what a functional is, right? So this is not for you guys because you all know what it is, but a functional is something that takes a measure and turns it into a number. Examples of functionals are the expected value, the variance, the entropy of the density. You can come up with anything you want. And if I wanted to have a Wasserstein gradient flow, I would have to say that this thing, x dot is equal to the gradient of something, would have to be the gradient of the first variation of mu at x. The first variation is essentially the Fréchet derivative of this functional. It's just some calculus called autocalculus. I'm not going to go into those details. And the reason why I want to see a Wasserstein gradient flow is because, well, if this is a Wasserstein gradient flow, what it means is that I can have now a variational perspective on what's happening. A gradient flow is trying to maximize or minimize something. And so if I have a Wasserstein gradient flow, it would be trying to maximize or minimize this functional. So if I can identify what functional I have, then I could say, okay, let's look at what the maximizers or minimizers of these guys are. All right, so here I have a reverse gradient flow, right? It's positive. So I could hope that mu is going to this argmax, right? The maximum variance or the maximum entropy or the maximum something if I find the right functional on the sphere. And so I started hammering at this. I was like, okay, what is this log of integral, the first variation of? And then it turns out it's not I was struggling, and it turns out that it was proved that it is not the first variation of anything. Gabriel Perret and his group, before we looked at this, actually had a similar perspective on this, and they said this thing lacks the symmetry that it needs to become a first variation of anything. And so from there, they went on and they modified attention. They proposed something they call syncformer to actually building some symmetry. And so they said, let's modify the architecture so it is a Wasserstein gradient flow. I didn't do this. I said, okay, I still want to show that I'm going to this thing is still a gradient of something. I don't know what it is, but it's still moving in some direction. And so I went back to the drawing board and I said, okay, this is the thing that I have. It's not the first variation of anything. But if I'm maximizing that thing, log is a monotone function. So let's see what happens if I don't have the log, right? Is that the first variation of something? It turns out, so what it means is that the dynamics I would look at are not the ones that I described to you. It's the same without the denominator, right? When I just take the gradient of the function rather than gradient of the log, I just don't have f in the denominator. So I just removed it. So it's the same thing without this normalization, and we call it unnormalized self-attention. And so now I'm actually indeed the first variation of some energy function, which is this weird interaction energy. It's this double integral of mu against this kernel k of xy, which is a Gaussian kernel. Everything's happening on the sphere, but it's just this interaction energy. It's a repulsive interaction energy, in fact. And if you start looking at the literature, you've seen this thing has appeared before. And people have been very interested in the minimizers of this energy function. So I like this paper by Yanshu Tan, who provides a nice simple proof of some results that were known since the 30s, that if you were to minimize this over all measures on the sphere, the minimizer, since it's repulsive, would make it the uniform measure, like basically as spread out as it can be. That's easy. That's not difficult to prove. What's more difficult is what happens if I actually constrain this measure to have finite support. Let's say I say, what is the minimizer of this functional over all measures of support of size n? And now you move from, I don't know, IEEE to Annals of Math, and this is very difficult. In fact, people don't know much. They only know for very specific values of n, of the dimension, and in fact, you even have to impose what is the pairwise angle that you want on the solution that you want to find. And you get those optimal configurations that you hear about when you talk about sphere packing, right? You have this Kissen configuration, Leach lattice, which was featured in Biazovska's Fields medal. All these things that are optimal configurations. So here it's on the sphere, it's not on the RD. But those things are very difficult, and we really don't know what's happening. But we're not minimizing the energy. We're maximizing the energy. And maximizing the energy is a one-line exercise. If you look at this functional, what measure on the sphere maximizes it? Well, you have e to the minus something positive. So you want this something positive to be as small as possible, which is 0. And the only way you can make it happen is by taking mu to be a point mass. If mu is a point mass, x is equal to y always. And so this norm squared is equal to 0. And therefore, you're going to have that the global maximizers are only the Dirac point masses. That's a single cluster. Okay, so that's good news, right? Because if I want to show that there's clustering and the global maximizer is clustered, then I have to just show that I'm actually converging to the global maximizer. So let's just pause for a second and recap and see where we're at. So we started with the self-attention dynamics, which was this gradient flow, which was not a Wasserstein gradient flow, and we said, okay, let's just study something different, which is unnormalized self-attention. This one I can say something about. I know what the global maximizers are. And how they relate to the original attention, in fact, is if you actually look at what's happening, if you were to actually put back those three matrices KQV, the thing that would change those dynamics is that you would have a preconditioner, which would come from the V and the derivative when I actually take the gradient, like there would be some matrices dropping out. So there would be some preconditioner, I'm going to call it W in front of both of them. And the way I actually measure the distance between x and y would be in some sort of learned geometry. There would just be some matrices that say, I don't look at the classical inner product, I just do I look at some Malahanobis distance kind of thing. Okay, so that's the same thing, except that I have a preconditioner and I have a different metric. And what we also saw is that this unnormalized self-attention is the reverse Wasserstein gradient flow with respect to, reverse gradient flow over probability measures with respect to this Wasserstein distance. And then we went back and we realized that in fact, this guy is also a reverse Wasserstein gradient flow, but not with respect to Wasserstein distance, but with respect to a modified Wasserstein distance. And in fact, you can come up with an arbitrary number of such modified Wasserstein distance, and Wooch and Lee has a paper in 21 where he does it, and you can think essentially as just like the entire family of Hessian metrics that you could put, right? There's an easy way to turn Euclidean metric into Riemannian metric. You just take the Hessian of some function, right? And then it's the same thing in Wasserstein space. So this guy is also climbing the same energy function using a different algorithm, which is more in a, like, think of it as like mirror descent rather than just doing gradient descent. Okay, that's basically the idea. So turns out if you run those things on, say, so this is tiny stories on nano GPT, so something I can run, it's like 250 million parameters or 200 million parameters. They actually have the same curves. They behave the same. Whether I have the normalization or not doesn't really matter. I'm not making any claims for larger transformers, but this normalization really doesn't change much about the performance of this transformer. Another thing I wanted to mention is, for those of you who are like, well, you remove the MLP, is the MLP really like the most important part? There's something interesting, which is, so the MLP is important, but not as important as the attention, in fact. So you see the curves on the top, the yellow ones. This is when I train the same transformer without attention at all. So I remove the attention, I have basically the same number of parameters, they're all in MLPs, but there's no interaction, and it just plateaus out, right? It just doesn't really go anywhere down. Now if I start adding attention, so the bottom one is some baseline, basically, and so that's the gray one is the baseline where I use the vanilla model that you can download from GitHub. And then I start like amputating it a little bit. The one that's the blue one is actually interesting. That's the one where I actually force those matrices to be identity. So it's a really stupid attention. That's an attention that actually does not have any parameters, and yet it has a drastically better behavior than pure MLP. So just this clustering properties of attention is really making a big difference in the possibilities of this transformer. Okay, so that's just, that's going to be my last numerical experiment, if for those of you who are feeling a little faint. So now the question I want to ask is, does gradient flow get trapped in some local maximum, right? I mean, I'm hoping to get to this clustered phenomenon, but maybe I'm going to get trapped along the way. Are there any local maxima? So to get some ideas on how to actually understand this, we're going to start with the 2D example. So in 2D, so my sphere is now in 2D. It's not realistic at all. But in 2D, there's something nice that you can do is you can actually parameterize those particles by their angle. And so you're not on the sphere anymore. You're really on the interval 0 to pi and wrapped around. And now you just have to do some change of variable. And you can actually do the change of variable for this. And it would take anyone 25 years old probably an hour. It took me a day. It took probably ChatGPT 10 seconds. And you do that change of variable, and this is what you get in terms of the dynamics that you incur for those arc cosines rather than just the positions. And so you can see there's those sines and cosines that appear. This is the self-attention with the normalization, a normalized self-attention without normalization. And the reason I'm showing you this is that if you were to actually remove this e to the beta thing, let's say you take beta equals 0, all right, so the exponential goes away. You end up with something which has just a sign, and this is known as Kuramoto oscillators. So I know it's not a standard thing in this community, but it's something that my colleagues who do more physical applied math are very familiar with. And it's the sort of bread and butter. It's the Gaussian sequence model of interacting particle systems. All right, it's really the test bed that people are really trying everything on, and it's just having a bunch of particles that interact with other particles through this interaction kernel, which is the sign of the difference of the angles. Okay? And this is actually a model where so Kuramoto proposed this model in the late 70s, and it's really a synchronization model. They call it synchronization when all the particles end up in the same position. And so that just shows you the difference, right? So Kuramoto, we know that those things cluster. It's been known, actually not that long ago for some reason, but it's kind of known that you don't get trapped in local maxima. You go to a completely synchronized state. And the difference is that beta is equal to 0 there, okay? And so we're going to crank up that beta and see what the effect of it is. And so it turns out that you can show, so this was a known result in the literature for d larger than 3. For some reason, it did not work for d equal 2, which was more technical. So we proved it for d equal 2. I mean, Andrew Yao, who's a student at MIT, proved it. And so if d is larger than in any dimension, every stationary point is a saddle point. Okay, so that's what you can prove. And the way you do it is you say, let me place myself as a stationary point, which is not the global maximum, and I will find an escape direction in which I can actually increase my objective value. And you can get, using completely standard arguments here, you can conclude that if you start from a random dimensionalization, you're going to converge to the global maximum, which is this single cluster. And so that's great, right? So you show that you converge to a single cluster. And so here are the takeaways. You can do that guy or that guy as t goes to infinity. For any beta in any dimension, you will converge to a single cluster. But of course, this does not tell you how long it's going to take. And in particular, you might get very close to a local minimum and move very slowly through a stationary point for a very long time. And this is actually what happens. And if you remember the demonstration that I showed you, we had multiple clusters, not just one, right? We had multiple clusters. And it's important for a transformer to not collapse everything to a single point. It would lose all of its expressive power. You still want to have something. It's collapsing information. It's really distilling information, but it does not want to collapse it to a single point mass. So to understand the rates, we're actually building on work that's been done for Kuramoto. And so the work for Kuramoto was done in the mean field infinite token limit. All right, so I start with some IID tokens, and the way I can think of them is, as the number of tokens grows, I can think of having a full-blown density of tokens on the sphere. And for Kuramoto, it was done on the circle. So think about having a density on the circle, and you want to see how this density evolves. All right, and if it goes to a point mass, then you know it's been clustering. And so the density evolves according to what's called the continuity equation. It's just the PDE that governs the evolution of the density of particles that are subject to some velocity field xt. And here xt depends on μt itself. So it's a nonlinear PDE. And I start with a density, something that has a density with respect to the uniform measure on the sphere. I need one parameter. So the problem is that if I initialize at the uniform, nothing's going to move, right? And so I need to basically kick it off the hill, essentially, so it starts falling down. And the way I kick it off the hill is by ensuring that the initial average is not 0, okay? It just means that I'm like somewhat preferring a particular area of the circle. And what Morales and Poyato proved in 22 is that for the Kuramoto model, so beta equals 0 on the circle, right? D is equal to 2. In that case, this thing is falling out to a point mass exponentially fast. In fact, I mean, it's kind of shocking the dependence that they get in R0. It's like essentially 1 over R0 squared. The exponent is really nice. And it's exponentially fast, right? So there's some burnout rate at the beginning where things need to start moving all on the same hemisphere. And once everything is on the same hemisphere, it's going to contract exponentially fast. It's not like a vanilla strongly convex thing that you typically analyze for this, or it's not even a Polyakloyasevich type inequality. It's actually pretty complicated. You have to really make sure that you keep track of the mass that's on the wrong side of the hemisphere, or the circle in that case. But they managed to do it. And at the price of much effort, we're able to extend it to any dimension and to some positive beta, but arbitrarily small, essentially. And the reason why is because our proof is essentially a perturbation of their proof where there's like a lot of additional terms, and we have to make sure they're not getting in the way of the proof. And so you can show that this thing, and so you can see now the dimension shows up here, the R0 is no longer 1 over R0 squared. I mean, all these things become much worse, but you can still get this exponential thing if you're in some perturbative regime of Kuramoto. But I think really the main message is that you can extend their result to larger dimension. The beta positive is really a minor improvement. And the reason why you have to actually constrain beta to be small is because it's not true for larger beta. It's just you don't have exponential convergence. In fact, for larger beta, you can come up with things that satisfy this R0 positive that actually don't converge to a single cluster.
Understanding, so T, time T.
Yes.
What is the meaning of T? Because you have some explicit constants, and then just what is the nature of scaling? So T, is it related to number of iterations?
Yeah, so that's a good question. You could ask, is T, so the thing you want to think of is that T is the number of layers, right? But it's not necessarily true, right? I could actually run those dynamics for unit time. And in fact, if you give me 100 layers, I would just have a very fine discretization of the unit interval. Or I could just have like this one-step thing and go to time t equals 100. I don't know. And what I think is actually happening is that the transformer trains itself, right? And so what it does, it decides what actual t is. And I think it basically, t is essentially the time it takes to go to the first stationary point around which is going to get stuck. But this is a bit jumping the gun because I have not told you that I'm going to get stuck for a very long time close to a stationary point.
I just want to understand, so this T over 100.
Sorry, this is the 100 you're unhappy with? Because that's a proof technique. That's a proof. If you want to improve that 100, please go ahead.
How long I should wait until it is small?
101?
It's still not small. So what does it mean?
I mean, we've been discussing for 101 seconds right now, and I'm going to start moving on. But okay, so it turns out that for any beta, you cannot prove this for any beta, and there's a very complex structure that's happening. So I'm not going to discuss this in details. There's a really nice paper by Bruno Pasqualotto and Agazzi that was presented at NeurIPS this year. And they study the beta goes to infinity regime. Okay, so they start with the mean field, and then they let beta go to infinity. And in the beta go to infinity, some of the things start simplifying. And so for large beta, so think about it as very large beta. And so for this very large beta, they can actually show that there's some sort of a saddle-to-saddle dynamics that's happening. And essentially, first your points will collapse to some great circle, say on the sphere, and then those circles are going to start clustering into multiple clusters, and then those clusters are going to match one another, one after the other. Okay, so we also have a paper where we studied that last part here, not the first phase, but more the last phase. And if you actually run experiment, this is on the sphere, those are real self-attention dynamics, and you can see that, you know, those things get stuck in this thing for quite a bit of time, and if you wait long enough, you will see that two clusters start, you know, collapsing with each other, but they're moving very slowly right now. And so this is reminiscent of some phenomena that happen in PD that are related to the Allen-Cat equation. So there's this coagulation type phenomena that arise where, you know, similar things where clusters start collapsing with each other, and people have studied this kind of things and we're reusing those tools. But the take-home message is that this is what's happening. So if you start with some sort of a pre-clustered state where you're not uniform, we don't know how to say how it starts from uniform, it's too chaotic. It's like starting too close to the top of the hill. But let's say you're a little further down the hill. Let's say something that's sort of pre-clustered like this. Pre-clustered means that things are closer to 1 over square root of beta range with each other in a cluster and farther than 1 over square root of beta away across each clusters. And so that's the scale at which things are happening, 1 over square root of beta. Then if you start from here, you're going to very quickly in time beta have those things cluster. All right, they're going to get very tight very quickly, and they're going to be e to the minus beta order beta of each other close. And then you're going to get stuck on this thing for exponential beta time. All right, so you're going to be stuck there, and then you're going to start having, it's like if each of the clusters was now a new particle, and the new thing is going to happen at a new scale. And so you can actually find exactly at what scale you need to change. So now t is at e to the beta, so things are essentially, so beta becomes e to the 2 beta, if you will, beta becomes 2 beta, if you will. And so you get this saddle to saddle dynamics that's become sharper and sharper as beta goes to infinity, essentially, where this is the kind of plus that you see when people are studying saddle to saddle dynamics in some, say, diagonal neural networks and things like this. Okay. How much time do I have? 5 minutes. Okay. So this is for the clustering things. And I want to get, so that's all I know how to say in the general model of self-attention that I've described. And I would like to have finer features. And to have finer features, I actually need to move to an even simpler model. right? And so what is an even simpler model? We kind of came across it somewhat accidentally. And this is a model where you start with your particles, your tokens, equiangular position, all right? So they're all in this completely symmetric model where the pairwise distance between two tokens is the same, right? So this is not going to happen in practice, but the reason why we study this model is that if you start like this, you stay like this at all times. So they're symmetric, they stay symmetric up until they collapse to a single one. And what's nice about this is that I have only one parameter to keep track of, and it's this pairwise angle rho t, which is the same for all pairs. And I can write the evolution of this pairwise angle. Right, so you just write it, it's an ODE. I can solve it numerically. I don't know, or I can even look at how fast it's converging. So this thing, what we all know is going to converge to 1 exponentially fast. So I can look at this and I can prove it. So for example, you can show that this rho t, that's the rho t is converging exponentially fast. So rho t is 1 minus the angle. So 1 minus the pairwise angle. So it's converging exponentially fast. And we used it to actually study what would happen if we were to initialize close to for IID points, which are close to orthogonal. And you can see this is what's happening. So that's the phase transition from not clustering to clustered. And you can see the black line is this solved ODEs, and the white line is what actually happens when you don't have infinite dimension, where they would be perfectly orthogonal. But the reason why this is actually interesting as a model is because we can study more fine-grained things like different normalization schemes. So I'm not going to go into details, but the normalization that I described where I force my tokens to stay on the sphere is not the only way people do normalization. They have all sorts of names like post-LN, that's the one I talked about, pre-LN, peri-LN, NGPT, all those sorts of scalings. And in this model, you can actually show, in any model, you can actually show that in fact, this just corresponds to the same dynamics with some speed regulation factor. So if you think about, well, I'm not going to go into too much details, but for that, you only need to track the direction of the tokens, right? So I look at a token, it has a direction, and now it's free to live everywhere. So I'm looking only at the direction, and if I track only the directions, which is now a vector on the sphere, it's just moving slower depending on how far, for example, the token is from the sphere. And this is something that's easy to imagine, right? Think about it. Your token is going to infinity. I'm only tracking its direction. So even if the token is moving a lot, its direction is not going to move fast, right? And so that's what this thing is doing. That's, for example, for pre-LN, that's what's happening. And you can do all of those guys in the same way. And what we did is we said, okay, let's use this symmetric model to study how we can actually compare and maybe give some prescription about which normalization to use. And so for all of those guys, you can write the rate at which in the symmetric model things actually collapse. And it turns out that people looked, when they proposed variations around the post-layer norm, they said, well, there's something that's not nice about post-layer norm is that if I were to actually look at a train transformer and kill the last, say, 15 layers, nothing would change. And the reason is because at the last layer minus 15, I'm already clustered. And so nothing really is changing. And the reason is because I'm clustering too fast. And so if you actually zoom in on those guys, you want some normalization schemes that do not go to 1 too quickly. Those are the ones that collapse too fast. Exponentially fast is something we don't want. So that removes post-LN, the one I've been talking about, NGPT and LN scaling, and there's 3 of them that are actually polynomially fast when they actually cluster. And if you actually now, what you can do is see how fast they're actually moving away from 0. So here you actually want to be not too lazy in the initial layers. And there's a winner if you actually combine those two guys, and it's this thing called peri-LN, which is implemented in those GEMMA models that Google has released earlier this year. And in the 2 minutes that I have left, I wanted to also mention how this simpler model is useful to understand what's happening in long context, right? So the context length is n, the number of tokens. And I don't know if you've used ChatGPT, but if you've always stay on the same chat, you realize it's becoming really slow. And there's some issues that it just has to remember a lot of stuff, and people have a hard time, tuning those models to actually handle a lot of stuff. And so Claude, for example, Anthropic in August announced that now their Sonnet 4 model supports 1 million tokens of context, meaning that I can ask it anything about 1 million previous tokens and it will remember them. It will keep them in RAM, if you will. And so people try to find ways to sort of scale models that were trained on short context to make them work on larger context, right? Because the context in which they're trained is basically batches of data, and that's just, determines where they work. And one solution that they proposed is just to multiply this guy by some beta that grows with the context length, Why? Because beta, remember, 1 over square root of beta tells me how far I need to look, right? And so if I have more tokens in there, I should not look as far because I'm just paying attention to too many stuff that's close to me, right? My neighborhood of sites 1 over square root beta is just becoming too crowded. I really want to do KNN. I don't want to do KDE here. And so it's just getting too crowded. And so what people said, they said, okay, let's just make beta larger. And somehow, so that was the first proposition, take log n squared. And then people started converging to this log n. And the question we asked is, so how do they convert to this log n? What they do is like for every n, they just find what the optimal beta is, and then they fit it to a curve, and they find that a log n curve, order log n curve, is what actually matters. And so that's the way they do it. And the question is, can we just explain this using the contractive properties of attention? Is it the case that this is a sweet spot before which I'm contracting too much, after which I'm contracting not enough? And it turns out that is going to be the case. I'm going to go quickly on this. So essentially, we're doing only one layer of attention, where we start with 2 angles, and we're going to get 2 angles outside of the attention layer, and we want to know if those guys get smashed together, don't move, or move somewhere in the sweet spot. And so I don't have time to give you the intuition for why this is actually log n, but what we essentially can prove is the following. So this is at a scaling, beta is equal to gamma times log n. Okay, so I'm already at the scaling log n, so I'm right, beta is gamma log n. And so I really want to show that something happens on this scale. And what we show is that there is a sweet spot gamma for which something interesting happens, but if gamma is too large, right, so meaning that if beta is too large, I'm actually looking too close to me, nothing happens. I'm only looking at myself, the other guys don't have any impact on me. But if gamma is too small, I'm looking at too big a neighborhood, and I'm actually in the Kuramoto setting where everybody collapses to a single point. And so this is kind of a justification. You can actually verify it numerically. Sorry, I promised I wouldn't do that. But you can verify that this is where the sweet spot happens. So I'm out of time, so I'm going to skip with the connection. So I mentioned multiple times that this kind of looks like a KDE, and people have actually studied some clustering algorithms based precisely on trying to chase the modes of a kernel density estimator. This is called mean shift clustering. And this one where we recompute the KD every time we make a step is called blurred mean shift clustering. So people have studied the mean shift clustering where you compute the kernel density estimator once and for all, and then you just go to the mode. But to make it faster, people recompute the KD at every step. And you can hope that the number of modes of your KD will drive the number of clusters. And we wanted to try to study this to understand the number of clusters that we would get as a function of beta. And what we found is that it should be of order square root beta log beta, which is consistent with numerics. And the first time I presented this at Oberwolfauer, Enno was in the room, and he came very nicely and he said, "You didn't say you're wrong," because it's Enno and he's a polite man. But he said, "Well, I did prove in '92 that in fact this is not going to happen. You have IID Gaussian data, the number of modes should converge to the mode of a N01, which is precisely 1. So how do you get something which is, beta is 1 over the bandwidth, right? So it's polynomial, so this should be something that's polynomial in N. And so what Enno did though is that he said, I'm going to look at the number of modes that I have only in some bounded interval around the origin, which makes sense, right? Why would you look too far? Your Gaussian is going to be -3 and 3. But what happens is that if you start drawing Gaussians, they're going to become larger and larger, and this is going to be isolated points that just make all the little bumps. And in fact, this contribution, square root of beta log beta, comes from points that are not close to the origins, but are points that are log n away from the origin. And that's how you get all those bumps that contribute to that number. All right, so I'm going to stop here. I have some conclusions that essentially in black say it's an interesting model, look at it. And in red, those are future directions of research we're currently actively pursuing, and I'm happy to chat about them if you like. Thank you for your attention.
Thank you, Philippe. We have time for one very short question.
I have a question about if you're, by the way, very nice talk, very interesting. And if I actually have different query matrix and the key matrix, does that mean my algorithm will have another limit other than a single cluster? That's the first part of
it. Oh yeah, definitely, right? Because you're changing, okay. So here is an example where you won't have a cluster, is if you take V to be negative identity, in which case you're actually doing actual gradient descent. So your particles are getting pushed away from each other, so they don't tend to contract. It just so happens that by picking V identity, you're capturing sort of the average thing that's happening along the way. So what you can do is study the case where those KQVs are random and try to understand what's happening there. Are you capturing some sort of average phenomenon? And yes, you can. But in practice, things are clearly deviations around this ideal model. And more importantly, in this model, I also said that you're converging even in practice. Even in the real time, you will converge to multiple clusters, not just one cluster, right? You're going to get stuck there. And that's what seems to be happening in practice, but they're not completely tight clusters. They're sort of like, sort of blurry clusters where tokens are not perfectly clustered, but it's sufficient for the transformer to do its job.
Does that mean that if I care about feature learning or prediction, then I should pay more attention to the a multi-cluster stage instead of the limiting behavior?
Yeah, that's definitely the one that matters in practice, yes.
Thank you. Let's thank Philippe once again.